Hello everyone, this is Likith Kumar. Welcome back to my channel, and today we are going to talk about one of the most important, dangerous, and frequently discussed topics in computer science and cybersecurity, which is buffer overflow, a vulnerability that looks very small at first, but has the power to completely break a system if exploited correctly. So let us start from the basics in a very simple and clear way. In computer programming, a buffer is a temporary storage area in memory that is used to hold data while it is being processed, such as user input, file data, or network packets. And every buffer is created with a fixed size, meaning it can store only a limited amount of data. But the problem begins when a program does not check how much data is being written into this buffer. A buffer overflow occurs when more data is written into a buffer than it can hold. And this extra data does not just disappear, instead it spills over into adjacent memory locations, overwriting important information such as variables, control data, or even function return addresses. And this is where the real danger begins. Buffer overflow vulnerabilities mostly occur due to poor programming practices, especially in low-level programming languages like C and C++, where the programmer has direct access to memory, but the language itself does not automatically check boundaries. So if the programmer forgets to validate input length or uses unsafe functions like gets, screpy, or scanf without size limits, the program becomes vulnerable. To understand how buffer overflow actually works internally, we need to understand how memory is organized in a running program, where memory is divided into segments such as the code segment, data segment, heap, and stack, and buffer overflow attacks usually target either the stack or the heap. In a stack-based buffer overflow, the buffer is stored inside a function on the stack along with local variables and the return address. And if an attacker provides carefully crafted input that exceeds the buffer size, the extra data can overwrite the return address, which tells the program where to go after the function finishes. And by overwriting this return address, an attacker can redirect program execution to malicious code, often called shell code, which can give the attacker complete control over the system. Heap-based buffer overflow attacks, on the other hand, occur in dynamically allocated memory, where overflowing one heap buffer can overwrite adjacent objects or metadata, leading to memory corruption and potentially arbitrary code execution. And although heap overflows are more complex to exploit, they are still extremely dangerous. One of the reasons buffer overflow is considered so serious is because it can lead to remote code execution, meaning an attacker sitting anywhere in the world can send malicious input over a network and take control of a system without physical access. Historically, buffer overflow vulnerabilities have been responsible for some of the most devastating cyber attacks, such as the Morris worm, Code Red worm, and SQL Slammer, which spread rapidly across the internet by exploiting buffer overflow bugs in widely used software, bringing down servers, networks, and even entire regions of the internet. Even in modern times, buffer overflow-related issues continue to appear, sometimes in different forms like buffer overread vulnerabilities, which can leak sensitive information such as passwords, encryption keys, and personal data from memory. The impact of a buffer overflow attack can range from simple program crashes to complete system compromise, data theft, malware installation, and privilege escalation, which is why it is considered a critical security issue in operating systems, embedded systems, web servers, and IoT devices. Despite being a decades-old vulnerability, buffer overflow still exists today because legacy code is still in use. Performance-critical applications still rely on low-level languages, and not all developers strictly follow secure coding practices. To prevent buffer overflow attacks, developers must validate all inputs, ensure proper bounds checking, avoid unsafe functions, and prefer safer alternatives. While modern systems also implement multiple layers of defense, such as stack canaries, which detect stack corruption, address space layout randomization, which makes memory addresses unpredictable, and data execution prevention, which prevents execution of code from data regions of memory. In addition, static and dynamic analysis tools are used to detect buffer overflow vulnerabilities during development and testing, while runtime monitoring and sandboxing help limit damage even if an attack occurs. From an educational and ethical hacking perspective, buffer overflow is taught not to encourage illegal hacking, but to help developers and security professionals understand how vulnerabilities occur, how attackers think, and how secure systems can.